out. Okay, we are on. Welcome back to experimental learning, experimental design for machine learning, and let's just dig right in. So first of all, remember my office hours on Monday. Thanks for some people showing up. I think we have a very good discussion. Please use this. Office hours are very, very good, especially for discussing the homework and asking questions. I know this material right now is very dense. Okay, this is absolutely clear to me. And so the idea obviously is that I present the dense material right now, and later that gives you enough time till the end of the semester to chew it while you're working on your project, and also while you're in my discussing with me and your peers, A, on Piazza, and B, in the office hours. Okay, I am very aware that this material is dense right now, and it's gonna start to get less dense from now on, basically, and that makes everything a little easier. But also, we're gonna use, obviously, what we introduced earlier pretty intensively, which also helps you understand it better. So again, thanks for bearing with me until now. And what will happen is we'll get, a lot. We get less and less dense, which helps, I think. So now, for the project, I put a project description on Piazza, so everybody should know what it's about. Please ask me questions. Please form teams if you can. I realize it's COVID and it's a lot harder. But one thing you could do is you could think about a project you want to do, and then with the project descriptions, and you just post it and you say, hey, I want to do this. Anybody join in? Right? So it's a little bit of it's a little bit of an online market thing. It's kind of weird, but the point is, I think that's the way to go with COVID right now. So I really just invite you to post and say, okay, I want to work on this. Does anybody want to help in? And some people will have ideas that excite other people. Some people will just work on their own. I think the best way is to just figure out on your own and then see if people want to join in. And that's how you meet other people, at least online. So please, basically, let's start forming teams this way. And again, please send me any questions about the project descriptions on Piazza. So any questions about project right now? Joining? Okay, any questions about projects? So if there are no questions about projects, because they also, do end of the semester, so and the semester just started, any questions about the homework? Anybody looked at it? I do know that people looked at it. I got a bunch of questions. Any questions about the homework? So then I have a question for you. Do people prefer we go through the homework here in lecture, or would you rather do it in office hours? Or would you rather have me send you a solution? Should we do a poll? There's a way to do a poll. Let's see. Right, so what the heck? My mouse cursor just disappeared. Okay, it's back. So at a question, no, I'm gonna launch a, this is so weird. I'm gonna launch a poll. I don't need to add a question. This makes no sense. Okay, so polling. Okay, so this worked before. I don't know why. Okay, so homework. Let's see. This is okay. so let's launch the poll. Okay, so if you want to discuss the homework in lecture, choose option 1. If you want to discuss the homework in office hours, choose option 2. And if you want the homework, just I give you a solution, you don't care, then choose option 3.
Can we do more than one?
I wonder. Okay, so let's start with this one. So I feel like you want, okay, so okay, let's not do option 3 right now. Let's only do option 1, means you want the stuff discussed in lecture, and option 2 means you want the stuff discussed in office hours and rather power through lecture.
I have a question. Is it possible to get the solution of the homework, and then maybe if we have question, we can ask you in office hour or maybe lecture potentially?
That would be option 4. What do people think about? Okay, so, okay, first of all, what I see right now is most people would prefer to discuss this in lecture, right? Now, there's another option, which is, okay, so the office hour option seems to be smaller. And okay, let me end this. Okay, look, okay, share results, no. So let's relaunch this. Okay, so now that we know we discuss in lecture, should we discuss the full thing in lecture? Or should we just discuss questions after I release the solutions? So full thing would be option 1. Questions after I release solutions would be option 2. Okay, that makes a lot of sense to me. Okay, so that sounds perfect. Okay, so we all decided I'm going to release solutions, and then we actually go with that. I'm going to release solutions to the homework today, and then in next lecture we're going to discuss homework 1 solutions question to that, and I'm also going to release homework 2 today, but not the solutions, and then I'm going to release the homework 2 solutions next week, and we're going to discuss it in the lecture afterwards. Okay, thank you so much. That helps. You know, that seems like a good idea. Okay, good. So yeah, I completely agree. That seems, so I have the solutions for the homework, obviously, and all of this. So by the way, I never give homework I don't have the solution for, because some people do that. I don't. Okay, so I'll post then today the new homework for next week, but also the solution to this week's, and then next week we'll discuss the homework. Awesome. That's awesome. So, okay, so demo time. So I think we're gonna do the demo after the lecture, but it's really important that now we get to the point where we can start thinking about what's actually going on in that app, why does it make sense, what doesn't it explain, and a couple of things like this. So if you haven't tried the app yet, please do. There's a bunch of people in my group that are maintaining it and working to make it better and better, you know, as we go on. So reminder from last lecture, we had this very interesting curve, okay? This curve is from chapter 40 of the McKay book. It's figures, if you open the chapter, you'll see it. What it shows is on the x-axis, it shows basically the number of so the number of input dimensions, and on divided by the number of parameters in the perceptron, right? And of course, if the number of input dimensions equals the numbers of parameters, then it's 1. That means n equals k, but the interesting part is that it goes that k can be smaller than n. And on the y-axis, it shows the probability that all functions can be modeled, okay? So and it shows us three areas. It shows us the area n divided by k is between 0 and 1. What it means is you have more parameters in your perceptron than you have dimensions in your problem, okay? And n again is just the number of rows in your table for a binary classification problem, okay? So for example, if you just had 2 rows, right, then n would be 2. And if you know, one input dimension, then you don't know, but if k is 2, which is usually the case, which is 1 input dimension and 1 threshold, then n equals k, and that means, yes, the perceptron can model all binary functions of a single variable, okay? But then we also looked at 2 variable binary functions, and so n would be 4, and k was 3 because 2 inputs and the threshold. And then it became this function called tnk that is also described in the McKay book. And tnk was 14 for that number. So then 14 divided by 16, because we have 16 functions of 2 Boolean variables, would be less than 1, and that means there must be functions that we cannot model, and we figured out that is just the answer to Minsky's problem, that XOR and not XOR cannot be modeled. We also talked about what not XOR is, because it's a way more intuitive way to think about it, which was the equality, right? So you cannot model equality with a perceptron for 2 variables. So now, the interesting part here is, for me, there are lots of parts of this curve. I can spend probably an entire lecture bore you with this curve. This curve is an extremely interesting curve because it connects to physics, to chemistry, to a bunch of things. Just for your information, a physicist would look at this curve and would say, well, the cases where n are smaller than k is a solid, okay? So n is my energy, right? And k is some particle that absorbs energy. And of course, if the energy gets distributed, then nothing changes. Maybe it heats up, but it stays solid. I can still completely predict what's going to happen. And then physicists would say, and I'm actually not making this up, there's a lot of papers on this, n divided by k between 1 and 2 is a liquid. Basically what happens is, if you put enough n in, if you put enough energy in, things are going to start to melt and be sort of predictable. We kind of know what's going on because, hey, there's a water glass, right? So if you look at the ocean, like a water drop will not move from sort of, let's say, the position you have it in right now to like the other end of the ocean within a minute, right? But it may move in its surroundings, so it's kind of predictable, but not completely predictable. And then once you go over 2k, then you have the gas assumption, where you basically say, hey, we can't know anything. A particle may just move from A to B within no time, we have no idea, okay? And that's interesting too, to see it this way. There's also something very, very, very interesting, right? This curve describes n divided by k, right? So this curve also describes that actually, remember this curve is asymptotic, right? So after 2, there's still stuff going on. And it turns out that this curve never hits the x-axis. It's asymptotic. It hits the x-axis in infinity. And now let's go back from the physics and all of this to just us. What does that mean? That means there may be problems, there may be functions, there may be data, where let's say 1,000,000 dimensions can now be modeled by very, very few parameters. And that's very interesting because, wait a minute, it's not so fixed, right? So you get to the point where it's like, okay, maybe I can find a problem where there's so many dimensions, but then we need so few parameters. And the answer is yes. Very low likelihood to find this problem. Probability is very, very low, right? The probability is actually on the y-axis. The probability is very, very low, but you may be able to find one, which is kind of interesting also. So now the bigger problem for us is, again, two more things, and then we'll talk about the bigger problem. The other thing is the n equals k case obviously is the VC dimension. So the VC dimension defined for uniform random points is the n equals k point, right? So when you have a same amount of parameters as you have dimensions, you're good. And then the interesting part is that this sort of 2 is sort of the supremum of the mutual information, is the n equals 2k, is the Cover-McKay capacity, with the basically it's the information capacity of a perceptron, right? And so the interesting part here is that even for uniformly random points that are by definition uncompressible, the perceptron is able to compress it in expectation by a factor 2. Okay, so you only need half the amount of parameters to memorize even uniform random points than you would if you just memorize them. And that is very, very interesting. And that leads neurons to be very good sort of for generalization in general, okay? So we will go back to this curve a bunch of times, and it's gonna take a while, I think, for everybody to realize what this curve does. But one thing to do is to just keep it for now, and then I will tell you the experiments that we did over the last couple of years to actually generalize this curve from the single perceptron to a neural network. And I will explain to you how this works and how you get there, and that this curve is actually not just for the perceptron, it is completely universal for an entire neural network. But let's go there step by step. Any questions about this curve for now, just as it comes to your mind? Okay. One question that should come to your mind is, in which part of the curve should I be for maximum generalization, right? And of course, the answer is as far to the right as possible, right? Because then as few parameters as possible are memorizing your points. And that means you have ambiguity and may be able to also reason about points you haven't seen. Having said that, these are intentionally chosen to be very random, right? So point is, of all functions, the probability that you can memorize them, this is what's plotted here. So generalization isn't there yet, but you can see that if obviously you want to be on the far right as possible. Okay, now let's go from a single perceptron to perceptron networks, or multi-layer perceptrons, or deep learning, as we now call it. To be frank, we've been calling it a lot of things. When I did my PhD, they were called neural networks, and of course they still call neural networks, but you know, the difference has become that the layers become deeper and deeper and deeper. And then all kinds of tricks have been performed, like convolutional layers, do ResNet, use ReLU instead of sigmoids. All of these tricks just basically came as sort of tuning of the original concept. And for now, what we will do to keep things simple, we will actually tune out all these tunings, okay? For now, what I was interested in is, okay, I understand the perceptron now. McKay explained to me the perceptron. Okay, I see what it can do, what its limits are, how many functions it can implement. I have the curve, but what does that mean for neural networks? And the first thing you look at when you look at neural networks, it looks like this. There's the hidden layer and layer, and then there's the output layer and input layer. But really, when you study neural networks, you have to be careful. They don't only look like this. There's a bunch of interesting other architectures. Like ResNet was reinvented, I think, by Microsoft. Does anybody know? I think Microsoft turned it, right? But the interesting thing is, if you look at this, on the left, you see a typical two-layer architecture, input, hidden, output layer, that solves XOR, okay? So I actually invite you to try this. You will see it solves XOR, okay? If you just multiply through, you will see it solves XOR. Now on the right, we have another solution to XOR, and it's a neural network, but it's not a multi-layer network. It's a network that just looks like a ResNet. It's called a shortcut network, okay? So on the left, you see basically the typical thing, and it's also nice because you see all the values are just 1, -1, and the thresholds are just 0.5, right? It's a really nice, well-trained network. On the right, actually you see the interesting part is it uses less parameters. It uses, on the left, it uses 1, 2, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9 parameters, okay? So 9 values that have to be tuned. And on the right, it uses 1, 2, 3, 4, 5, 6, 7 parameters. And that's interesting, right? We also know from AK that T44 would have been 16. So that means if it was able to create a neural network that had only, or a perceptron that had only 4 parameters, I need to rephrase this. If it was able to create a perceptron that would accept 4 parameters, because I can't, right? Perceptron is input threshold gives us 3. How do I get the 4th parameter in, right? Doesn't work. So the reason here is that it was able to create a perceptron, right, that had 4 parameters. I will be able to solve XOR and not XOR as well, at least to memorize it. But since I cannot, I now need to revert to neural networks. So these different architectures give us the possibility to take in, to basically have perceptrons collaborate and solve things that a single perceptron cannot do. That's the reason why we do neural networks. But now there's a problem. Remember when I said on the K curve, where do we want to be for generalization on the most right? Well, we go from 4 parameters that we can't realize. So we go from 3 that we can realize to actually 9 on the left. 9 parameters. That's a huge jump. The discrete jump from 3 to 9, adding 6, having 5 too many, basically, okay? So that is, unfortunately, the dilemma. And if you think about it, yeah, often tasks that can be solved by, not to be solved by 1 person can be solved by 2 persons, but there's a lot of communication overhead. And that's the same here. What happens is if you want to solve XOR, there's a lot of communication overhead on the left. Now, that's why people thought about other networks. Can we just go, instead of use 4, maybe what's the smallest? It turns out what you see on the right is the smallest known solution to XOR. It's 7 parameters instead of 4. It's better than the 9, but it's still not the 4. So there is some overhead involved the moment you create a neural network. And what's the danger with that? The danger with that is that you use too many parameters and you may overfit, right? And that's inherently a problem of neural networks. Decision trees, for example, random forests don't have that problem. Okay, that's why so many, but if you want to actually keep to the idea of collaborating perceptrons as neural networks, then you have that problem. You may just need the communication, you may just need so much extra overhead, okay? So that's the first thing to understand. But the second thing is, and by the way, these 2 pictures are from the book from Raul Rojas, Intro to Neural Networks, which I also put the link on the website. So if you want to dive deeper into these networks, please do. Also, he has a very, very, very nice visualization and description of how perceptrons work, perceptron learning works, and also how the backpropagation works. Okay, so please try to look at this. So now the second part. The second part is, if I'm creating a theory, which I'm going to show you in a bit, that is to explain how perceptrons actually collaborate. So what is the joint capacity of collaborating perceptrons? Then my theory cannot assume just this architecture. My theory needs to be more general. It should explain mathematically why the right one is actually better or capable than the left one. And before we go there, there's no free lunch, remember? Nothing is free here. What's the problem with a network with less weights on the right? Any guesses? So left looks nice, but right, what's the problem? Any guess? Maybe Mesut? Just picking you randomly, you know I do these things.
It doesn't, I guess, it encode, I guess, it has more, a more structure to it, which makes it harder to train. I guess harder to learn. I don't know. I'm just making a guess.
You make a really good guess. It turns out the right one is hard to train. The left one is much easier to train. And why? Well, we can even explain that too, because if you have more parameters, you can sort of correct errors more easily, or can wiggle out things, right? Even if there's like a case, and we will talk about this when we talk about adversarial examples, even if there's a case on the left, which is kind of not so clear, the case on the right, so it allows to wiggle things out. The case on the right, you have to be really precise. And also, if you just look at the weights, right, or the entropy of the weights, it's clear that there's a higher entropy on the right than on the left. On the left, we only have -1, 1, and 0.5, sort of as an alphabet, right? On the right, we have 1, -2, 1.5, and 0.5, right? So that alphabet is already bigger. It's already clear that this is more complex. So yeah, funnily enough, while on the left, it's more parameters to tune, you will see that with a reasonable learning rate, you get there very quickly. And on the right, you will actually take a while and you might not get there. Now, you can try that out at home, obviously. But also, I will give you some homework where I want you to tune and actually come up with weights by yourself. Because these two networks were actually never trained. Somebody sat down and came up with weights by yourself. It's actually a very interesting exercise, and I can show you, or you will see when you do this practically, that on the left, you get there pretty quickly. On the right, it could be, it's hard, okay? I mean, do it outside, enjoy the air while you're doing it, okay? So, now, number two, as I said, is we need to explain both. So, how do we do it? Well, we were starting to measure in bits, right? So, if we look at each perceptron as a memory unit, right? As a unit that can memorize a certain number of lookups, basically from our table, or state transitions from our training table, right? We set that. So there's n rows of a table that we can memorize. Well, then we should have a memory capacity, right? So we call it the memory capacity. And this memory capacity, I will define from now on the n equals k case, okay? So why? Because me as an engineer, well, I find this fascinating how deep this graph goes. As an engineer, I want to be sure. As an engineer, I want to guarantee that I can do it, okay? And then of course, we want to see after we guaranteed that we can do it, that we move on this curve to the right as much as we can. But we're not there yet. For now, what I want is I want to guarantee that I can do it. And now guarantee that I can memorize all Boolean functions of two variables is to use a neural network with at least 4 parameters. Okay, and a guarantee that I can memorize all cat-dog classification problems of 1,000 dogs is to use a neural network with at least 1,000 parameters. Now, the big question is, however, does each parameter count the same? And of course, you will find that this is not true, right? Now, how do these individual perceptual memory cells actually behave, right? How does it actually work? Well, let's think of them as memory cells, okay? And let's start very, very, very simple. If you have 100 megs of RAM in your computer, and you add another 100 megs of RAM, how many megs of RAM do you have? Raymond.
Not sure.
So you have 100 megs of RAM and you add another 100 megs of RAM. How much RAM do you have?
You sum the two up.
Yes, 200 megs of RAM.
Okay. Is it like, okay, I thought it's like tricky, or I don't know. Yeah.
I know. I know. I wanted you to think, okay? I kind of formulated it as tricky. Now comes the real trick. Is that always true? What would happen if...
Probably not, because maybe not, like, I don't know, maybe not. Yeah, because like, I guess you can probably have more or less, or probably, yeah, less, maybe, I'm not sure. Yeah, but
Okay.
definitely not the...
First of all, also true, okay? And the reason I like that you say this, because again, what we do right now in this exercise of thought is we fix n equals k, okay? So I say, for 100 megs of RAM, you can guarantee that you can store 100 megs. You may compress it, right? Some memory cells may wrong, and so on and so forth, right? You may use inefficient learning, like backpropagation. Sorry, next time. But the major point is, you have 100 megs of RAM, you can store 100 megs of RAM. That's what we will say, okay? So you have a perceptron with 3 parameters, you can store, by guarantee, 3 Boolean classifications of sort of 3 rows of a Boolean classification, okay? So now the bigger question is though, what happens if I add another chip, right? I add another RAM chip, so you get to 200 megs of RAM. Yes, that's what it is. But the next question is that always true? Well, here's what's interesting. If I put them side by side and just allow the computer to address them as, you know, from 0 to 200 meg, obviously, then congratulations, you just doubled your memory. But what would happen if I put them in series? For example, you could think of this as a RAID scenario. What if you had a faulty chip, right? What you do is you put the first RAM in, and then the second RAM only reads from the first RAM. Why would you do that? Well, the point is you could always copy into the second RAM for error redundant code, right? So that you basically say, well, if my first RAM fails, I can detect that because the second RAM will then also, will not be consistent with the first one, right? So how much memory do you have then, still? So you take 100 megabyte and you put another 100 megabyte, but the second 100 megabyte is dependent on the first 100 megabyte.
Less, probably.
Yeah, you will have exactly 100 megabyte maximum. But if the RAM is faulty, and that's why you're doing it, by the way, then of course you have less, right? So if you put 2 RAMs sort of stacked below each other, you double it. But if you put 2 RAMs in sort of behind each other in depth, then you keep that memory, but you can correct errors. And guess what? That's the intuition we need to follow here when we think of perceptrons as memory units, okay? And now I will present you 4 rules that actually describe a neural network completely. So, first of all, the output of a perceptron is maximally 1 bit. That is rule number 1. How do we get there? Well, if you don't know anything about the perceptron, each perceptron is binary, right? If you don't know anything about the perceptron, it's 50% chance, right? And log 2 of 1/2 minus log 2 of 1/2 is 1, and that's 1 bit. If you know something about the perceptron, then it could be a 60-40, or it could be 30-70, but minus log 2 of, let's say, 1/3 or something, would be less than 1 bit. Sorry, it's would not be log 2. Sorry, it would be the Shannon entropy of that, you know, 1/3 and sorry, what am I saying? The Shannon entropy of that sort of 60-40 distribution, right? And the Shannon entropy of that will be smaller than 1 bit because there's less surprise than in the 50-50 scenario. The maximum surprise obviously is when you have the coin flip, right? But if your coin is biased, then there's less surprise because you have a higher chance to guess it right once you know the bias. So maximally, the output of a perceptron is 1 bit. And again, now we go back to the slides from the last couple lectures where you have to say minus log 2 1/2 is the same as log 2 of 2. Yes? Questions? Okay. Obviously, you may say, wait a minute, but what about multiclass? Yes, there are multiclass perceptrons, but right now we only look at balanced binary. So now, if you're unbalanced, then it's less than a bit, because then we have a priori a less chance. We already know it's not 50-50, it's maybe 70-30. So the information you get is even less. So maximally, a 2 fire or not fire decision is 1 bit. So each perceptron outputs 1 bit of information. And again, does the activation function matter? No, it doesn't. Because again, when we looked at it last time, it was like this curve, it really depends on how many points on the left and how many points on the right, right? So the output of a perceptron is 1 bit, is your rule number 1, okay? Now, the maximum memory capacity of a perceptron is the number of parameters, including the threshold, in bits. Now, where do we get that from? That is chapter 40 in McK. Because what you do is you take the log 2 t and k, right? Because again, that function gave us the probability of doing it right. So log 2 t and k would be, for example, for 4 would be 4, right? Because 2 to the power of 4 is 16, log 2 of that is 4. And that means for log 2, for t and k, for 3, 4, which was the sort of, 4, 3, the 4 rows of a 2-variable Boolean classification problem was 4. And then the k was 3 for the perceptron. It was 14. So we couldn't do XOR, not XOR. And then log 2 of 14 would be something smaller than 4, 3.8 or something. And that just shows you, yeah, most of them can be done, but not all of them, okay? So the maximum memory capacity of a perceptron is the number of parameters in bits. So if you want to guarantee that you can do all 4 rows, no matter what, of your binary classification problem, you need to use 4 parameters. Otherwise, it may or may not be able to be memorized, okay? So that's how you think about, that's rule number 2. And again, that is the whole thing with this T and K curve. And now here's the interesting thing. Number 3 is what we just discussed. The maximum memory capacity of a perceptron in parallel is additive. And the interesting part here is that McKay speculated this and said it's probably true in his book. You can see in chapter 40, there's an exercise. And what a postdoc and me in 2017 decided to do is like, well, maybe let's just do the exercise and I'll show you in a bit, okay? We did the exercise and yeah, it's absolutely right. So what happens is, just like 2 memory units where you add another 100 megabyte to another 100 megabyte, if you have 2 perceptrons, that gives you twice the capacity, maximally. Because there are some other constraints, like there's an output neuron that needs to be able to learn your functions, and we'll talk about that in a bit. So the maximum memory capacity of perceptrons in parallel is additive, okay? So 2 perceptrons will have 2 input and 1 threshold perceptrons will have 6 bit of capacity, not just 3. We'll talk about it in a bit. Now we are able to just basically put perceptrons into a single layer, and we say the single layer is just additive. But what happens to the next layer? What happens if we put memory in series? If you go from one part of memory to the next part of memory? Well, you said it. The maximum number of memory, if you have 2 100 megabyte memory chips and we put them in series such that the second memory chip depends on the first one, is still only 100 megabyte. Now, that's exactly true for neural networks as well. The maximum memory capacity of a layer of perceptrons, depending on a previous layer of perceptrons, is limited by the maximum output in bits of the previous layer. And the way to show this mathematically, and not just using sort of memory units, is there's a whole book on it by Tishby, published in 2012, about the data processing inequality. The data processing inequality says you cannot create information ever. You can only observe information. And that means if my layers of perceptron is only looking at the previous layer, fine. But it cannot create more information, so whatever it can store is the output of the previous one. There's no random inputs, right? So these are the 4 rules. These are also on the cheat sheet. This is how you can analyze neural networks. The app does it automatically for you, but let's go and practice a little bit with those 4 rules. Rule number 1. How many bits of maximal capacity on the left, okay? Well, again, what we do here is when I write these, and this is very important, this is also going to be for the homework, is that we assume that each arrow, input arrow, has a weight associated with it. And also each circle sort of has a threshold in it, okay? It's just what it is from now on, okay? So how many bits of capacity? Well, for the first one, it would be 3 bits because we have a W1, a W2, and a threshold. Now, for the next one, it would be a W1 and W2 for the first one, a W3 and a W4 for the second one, a threshold for the first one, and a threshold for the second one. And that gives us just 2 times of the first one, 2 times 3. That's 6 bits. But that's based off, rule 3. But now, based off rule 1, we know, okay, we only have 2 bits of output from that first layer, right? So we have 2 arrows coming out from that first layer. What that means is that we have only 2 bits out. Whatever these perceptrons do, there's 2 bits coming out. Each of them can say yes or no, right? It could be less than 2 bits. Maybe the second one only says yes all the time. But really what happens is it's yes or no, each of them. And that means that we have maximally 2 bits coming into that third perceptron, even though the third perceptron by itself has a weight on each input and the threshold. So by itself, it's 3 bits of capacity. But it's not really because it's limited. So it's only 2 bits. So the total capacity of this network is 6 bits plus 2 bits is 8 bits, okay? Because we're kind of wasting a bit of capacity of the second layer. Any questions about this? This is basically a way of going through neural networks like a circuit, right? Any questions?
Yeah. Why is it only 2 bits? Why is it limited to only 2 bits in the second layer?
Because of the same idea as what I said for the data processing inequality. You can't create information. Or if you think of memory, so the problem is this last one, again, by itself, actually has 3 bits of capacity. But it will only read 2 bits. So it would be foolish of us to count that into the complete capacity, right? It'll only see.
Oh, yeah, that makes sense.
Yeah, right. No, and thanks for asking, because this is really critical to the understanding that while each neuron obviously has the same capacity, if you want to know the overall, then you have to take into account the information flow, right? That's what the topology of a network gives you. And that's why we see, wait a minute, while there's the 6 bits of decision power or memorization power, it actually reduces it to 2 bits of the output. And even though the last one has 3 bits, it only sees 2 bits because it will actually see less than 2 bits, most likely, but maximally it sees 2 bits. And so you could just, well, disregard the third bit. So let's do that again. Now we go to deep networks. How many bits of maximal capacity, right? So the first one would be, again, each one is a perceptron again, right? So it's 3 plus 3, okay? 6 bits. But now it is interesting. Each layer itself, so the first layer has 6, the second layer has 6, and the last one has 3 by itself. But now taking into account the information flow, we'll see something which is it's 3 plus 3, and then, and that's interesting, how many bits are coming out of the second layer?
2.
Right. Why?
The output of a perceptron's only 1 bit.
Exactly. And despite the fact that we have 2 arrows coming out, they're the same decisions. So it's the same information, it's just redundant. So you have 2 bits of information coming out of the second layer, and that reduces the memory capacity of the third layer, sorry, of the second layer from 6 to 2. Because yeah, you could have 100 megabyte of RAM. If you only have 2 bits information to store, who cares about the remaining megabytes, okay? Let's call it 2 megabytes to store, right? So if you have 100 megabytes of RAM and you only have 2 megabytes to store, nobody cares about the residual 998 megabytes, right? So here's the same thing. Yes, you have 6 bits, but really you only see 2. So you can completely get rid of that in your total calculation. And what it means is you have 2 bits, and you have 6 bits plus 2 bits. And then what happens is in the output layer, yeah, there's again 2 bits. So we have the same math again. So it's 2 times 6, 2 times 3 is 6, plus 2 is 10. Any questions about this?
Yeah, I'm kind of confused. Like, so if in this graph we say there are 2 neurons in like previous layers outputs, then we only have 2 bits. Then, like in the last slide, the left graph. So in a single neuron, why would say it have 3 bits? Like there's just one. Wouldn't we also say like there's only 1 bit because the output is only yes or no?
So yeah, two things. First of all, one thing I forgot to say, which is important, is obviously the 3 bits of capacity are only there if you also have 3 bits getting in, right? So let's say your table only had 2 rows, your binary classification table, then you wouldn't actually have 3 bits. You only have 2 bits because there's not enough information coming on. But what we're trying to say is there's enough information coming on. That's number one. And what's important for us is how much of the classification of the training data can you actually store? Okay, this is what we're looking at. So what we store right now, we say the perceptron can do 3 bits. So for example, the standard example is you have 2 Boolean variables. 2 Boolean variables generate 4 rows of a classification table. And now the problem is you can't actually memorize all those 4 rows. You can only memorize 3. And then most of the time you can do 4, but you can't guarantee 4, right? So the important thing here is we're looking at a function compression. We're looking at how many rows can you memorize. So for a perceptron, you can memorize 3 rows. And of course, the output of your lookup table is a bit. It's yes, no, cat, dog, on, off, right? But the next question is, after we solved the perceptron, was what is the capacity of the overall neural network? And the capacity of the overall neural network, we could just be silly, and we can, actually, we were for a while, and we just add all parameters together. We just say, well, it's proportional to the number of parameters. And that's completely right, except it's too much of an upper limit. You want to get a tighter upper limit. And the tighter upper limit is to take into account the topology. And to do that, all you have to do is think about how much information can actually be stored in each of those memory units. And that's why we do that. So remember, what we're trying to model is a function from the input data to the output data. And our function always has binary output, but the question is, how much of the function can I store in each perceptron? And we measure that in bits because we know that if this function was sort of random balanced classes, binary classes, that knowing each row would be 1 bit of information. Does that make sense?
Yes, thanks.
This is this kind of situation where I would like to have a whiteboard and go in depth and discuss with you in classroom. What I can do is let me finish the presentation, and then I can start the whiteboard and stop the recording once we have time afterwards. And also, please do not hesitate to ask questions on Piazza, and do not hesitate to ask questions in my office hours, okay, if you do one-on-one. So it is very difficult. This is sort of the concept. What we compress here is the function and not just the data. So as we do that, again, we don't have to take into account the memory that we don't use anyway. That's the trick. Now that also explains why the shortcut network can do XOR. Well, it can do XOR because we actually have a lot of capacity here, right? So X1 has 2 weights associated with it, those 2 arrows, and then X2 also has 2 arrows, and then there's the perceptron. So the way I like to look at it is this. The first perceptron you see there on the left is just a regular perceptron, nothing new to it. So it has 3 bits of capacity, like all the other ones we had before. Now, what happens though is the second perceptron actually takes from the original input data. That means it is not dependent only on the output data, but it also reads the output data. The way I like to specify this is an informed decision, okay? So what you want to do when you ask somebody, you want to go and say, can you help me buy a car? But you don't want to make your decision completely dependent on his decision, because then your decision is only as good as his decision or her decision, the friend you asked to come with you to buy a car. But if your friend gives you independent input of his decision, and you also get all the input, then you can make an informed decision, and then you're better than you both. And this is basically what this does. The first perceptron is your friend, and the second perceptron is you. So the first perceptron gets all the input of the second perceptron, but also the second perceptron gets the output of the first perceptron as input. And so the decision is very, very, very nice. It's an informed decision. And what it means is that the first capacity, mathematically, is just 3, but the second capacity is the full capacity because rule 4 does not apply. Rule 4 would be the complete dependency, but no, we're not dependent on the friend. We are independent as well. And so that's why this is a very, very, very interesting construct, okay? So we get 3 bits of capacity because 3 parameters in the first perceptron, 4 parameters in the second perceptron, the 3 inputs and the threshold, and then 3 plus 4 is 7. So it's the maximum efficient way of representing the parameters. This topology is super, super efficient. And again, rediscovered by ResNet somewhere in the 2010s, I think, where they started to basically bridge layers with extra connections and then figured out, oh my God, training time takes so long. Yeah, it does, because you literally have to train both of them. Both of your friends, both the friends have to be educated in how to buy a car, but then they can help each other, okay? This is a very, very interesting construct. So Now the bigger question for us was, what happened if you try to plot a curve like this, like this curve from Mackay, not for a single perceptron, but for a perceptron network. And of course, the major point is that we should have come to the exact same conclusions that the rules that I gave you. And of course, the rules were derived by this. So the characteristic curve of an orthodox, there's a question. Give me a second. Yes, by the threshold, I'm referring to the parameter B. That is the decision threshold over the function that lies within the node based on the linear combination of inputs, right? So the threshold is just basically, you have the dot product, right? The sum Wixi smaller equal to B, that B is the threshold. Okay, go back to this. So, I probably have mouse cursor today, I'm sorry. Okay, so here's what's happening. What we did is, okay, we can now obviously try to get to arbitrary deep networks. But what we wanted to know is, what if we did, instead of a single perceptron and plot this, we plotted a 3-layer MLP, basically input layer, hidden layer, output layer. This is typical cookie cutter 3-layer network. And here's what's interesting. We plotted it against exactly the same way. So we plotted it TNK divided by 2 to the power of n, the probability for perfect classification, versus the number of samples, which is obviously our rows in our table, divided by k, which is the number of parameters. So it then turns out to be n divided by k is the same thing in Mackay. And it turns out, absolutely, empirically, you get the same curve. Because very important is that Mackay's curve obviously went up, goes up to this 2 point only in infinity. Okay, so as n divided by k goes to infinity, as n goes to infinity. Okay, so but the interesting part here is that for 2, it kind of goes down really quickly. For 4, it goes down less quickly, and so on. And the smoothest one is for K128. Now, this is what happens if you simulate this using our rules. But what happens if you actually use the real implementation? It looks like this. If we use a real implementation, you have to subsample. That's why you get the grizzly curves. But it still seems right. So what happens here is we use scikit-learn, and we plotted the same curve. We basically generated random functions, random tables, and then tried in number of hidden nodes, different kind of ways. And the input dimension was 4 for this one, but you know, as we add nodes, this thing became smoother and smoother and smoother, and obviously with 8 nodes, things got easier and easier and easier. The interesting part here is you can use this tool to actually find out how efficient neural network training is, because this network is a real network. It had to be trained with SGD. And of course, the networks don't change, but what does change is your hyperparameters, like your learning rate, all of these different things. And of all the networks we tried, scikit-learn was the best. Any guess what was the worst? Maybe I should turn the recording off, but no, I'm not ashamed of saying which one was the worst. Maybe Harrison, any idea what you think was the worst?
I have no idea.
I know I put you on the spot. I completely apologize for this, but just pick one. No, and maybe if you pick one, just based off rumor mill.
Which framework are you asking was the worst?
Yeah, which framework was the worst in terms of being able to learn functions?
TensorFlow?
That's a pretty good guess. Keras, which is part of TensorFlow, was. So Keras was actually the worst It was so bad in this test that it didn't actually, the curve here, caved in before 1. It caved in before 1. What it means is there's no way it can ever learn all functions. It's really bad. You have to over-parameterize some functions to even learn them. And it has to do probably with the regularization they put in and with the fact that Keras is optimized for images. But for me, that's a very bad sign. And of course, we know that Keras TensorFlow replaced it and was redone a lot of times. And they didn't have, they only had an intuition for there's a problem. We obviously have a measurement for there's a problem. So that is the characteristic curve of an actual 3-layer MLP. It looks exactly like a perceptron. And so now this is the interesting part. If you wanted to solve XOR, not XOR with a single perceptron, the constraint is that you need to use a neural network. You cannot do it with a perceptron. But what it means is that overall, the single perceptron is actually the best case. The one neuron case, information theoretically, is better in efficiency than the neural network. It's just a single perceptron can't do it all. You need to put perceptrons together to change this. And that's very interesting. Information theoretically, there's a lot of overhead involved, but practically, obviously, that helps. So let's sum this up, and then I'll be available for your questions. So we know that the worst case generalization is memorization, right? Memorization is a very bad way to generalize, but then we also know that you don't want to be doing double memorization, right? So what you want to be doing is generalization. So what it means is memorization becomes the upper limit for the size. And since memorization is well understood, it's measurable in bits, and we can actually go layer by layer and now with rules, just go through them, we just measure memory capacity. And we now know if we have a table of 1,000 rows and a memory capacity of 1,000, guess what? We know that in theory, this neural network should be able to memorize, aka overfit, the table. And now that's good because we now have a way of getting there. And now, yeah, that's the second bullet. The memory capacity of a neural network is measurable in bits. And I just gave you how to do it. And also there's exercises, homework you can work on how to do it. Now, here's the question. Why would you ever use more parameters than the memory capacity? Well, we answered it in lecture 2. Because if your training is hard, then you need more parameters. But there is a problem. If training is easy, then most likely you overfit because you have so many parameters. And now what I would do in this lecture, and I said this before in the earlier lectures, is I will say, let's assume our training is perfect. Perfect means if we were to memorize, we would only need the minimum number of bits to memorize everything, right? But what that then means is that, of course, we have a kind of warped theoretical view because SGD is far from perfect, and we just saw that in the curve. But it means that we could say we can guarantee generalization because we know that if we have less parameters in our neural network than we have in our training table, number of rows, then we actually can guarantee there's some generalization, right? So there could be generalization as well with a super huge network. It could be. But if you want to guarantee it, then we need to make sure we end up with less parameters in our neural network than we have sort of rows in our table, okay? And now there's this trade-off between training, generalization, and accuracy. Because in theory, if training is perfect, you can always reach 100% accuracy. The probability of modeling all functions is 1 when n equals k, right? But you want to be better than memorizing. At the same time, you have this shitty training that needs hyperparameter tuning, all of this. So how do you do that? Well, you can measure the efficiency just like we did, but also there's a lot more to come in the next lectures. Point is, from now on, what we know is at memory equivalent capacity, each machine learner should be able to memorize the function represented in your data, the training function. That's what it is. If you have n rows and n bits of memory equivalent capacity, you need to be able to get to 100% accuracy with overfitting. That's what we know. How do we not overfit? That's next lecture. But right now, I can tell you that I will consider overcapacity a waste of resources. And I will say overcapacity is not, oh, I use like 10%, 20% more parameters. Overcapacity right now with AlexNet and these things is they use 100 times, 1,000 times more parameters than you. And I don't think they need to do that at all. They're spending so many more resources training because they have so many more parameters. They're way beyond the trade-off where a couple more parameters help in training. But we will go into this in detail. So from now on, now that you know all this, I will say using a machine learner that is over capacity is a waste of resources and increases the risk of failure. And I will even go one more further. Alchemy converted into chemistry by measurements. It's a very sexy problem to say, I can convert lead into gold. It's a very sexy problem to say, I can take your shitty data and extract wisdom from it. But how do you really do it? Well, we know that we can actually convert lead to gold now. Physicists have done it. It's just a lot more expensive than finding gold, so nobody does it. Now, there will be data where it's really useful, where we really can extract wisdom. But then there will be other data where we cannot. And that decision should be made by measurement, not by try and error, because if we do it by try and error, it's just alchemy. And for me, that is data science. And I'm giving you a glimpse into this right now, but we'll go a lot deeper. And the moment you sort of internalize it, it's just the motivation for you doing the homework, by the way, is you look at machine learning experiments with completely different eyes, and you will see that you can actually go to 100 million videos on your laptop if you do it right. And that makes machine learning even more powerful than it already is. And we now actually started to think about ethical considerations, and that's something for Eleanor, but in reality, yes, there is some problem. Now, in general, that is where we are at right now in the thought framework. I'm hoping that you could follow it enough to this point, and the homework will help. Please go on Piazza Discuss. Please go into my office hours to discuss. And we will start in the next lectures to introduce slightly a little more, but we'll explain it with our examples, we'll explain generalization, and we'll explain how you can use all these simple tricks and formulas to actually build your experiment and to actually ballpark to say, well, so you have 1,000 cats and 1,000 dogs. Well, you don't need more than 1,000 parameters in your network, okay? But you may need layers. Why? Well, because images are harder than other things. Audio is harder than other things. That's something we also have to discuss. So that's the lecture after that, and then we get into very, very practical stuff. I will stop the recording here, and we'll completely open it to questions. I can open the whiteboard, or also I can show you a little demo, but also we can go. Give me a sec. Stop recording is my first thing.